Alright, so we reached tutorial 5. Today we're going to talk about modeling sequences. And specifically we'll show what RNNs are, recurrent neural networks, how they work. We'll implement a basic version. We'll show an application of classifying the sentiment in the movie reviews. And then we'll see an alternative, more recent alternative to RNNs, which is called temporal convolutional networks. Okay, so far we've seen these two types of models, these MLPs, composed of fully connected layers with prefixed input, prefixed output. You have to specify input features, output features. We've seen these convolutional layers, where each layer operates on these tensors with spatial extent and number of channels, and you have different convolutional filters. Each filter works on all the channels and kind of slides over the spatial extent to create one feature map. In this case, it would be a 2D slice. Okay, we saw these advantages of weight sharing and robust ability to use the different dimensions of input. However, there's one thing that sometimes we would like. We would like sometimes we have data that's a sequence. Okay, maybe frames of a video where there's actually meaning in the sequence. Okay, or words in text where there's meaning. So we want some way to represent this persistent state, the fact that the output now should depend on some previous input. Okay, so how can we model some kind of dynamical system? For example, in this case, a system where you depend the output at time t would depend on the previous outputs and previous inputs. Okay, so there's lots of use cases for this kind of modeling text, modeling dynamical systems. Like I said, video. So lots of ideas. So the classical deep learning approach, let's say, to do this would be to use recurrent neural networks. So the idea here is to have something very similar to a regular fully connected layer, but it has two inputs and two outputs. So it has one of the inputs would be the actual current input, the sample, and it would have another input representing the previous state. Okay, there can be different dimensions. So this state is just some vector. We treat it as an input, and it produces also two outputs, which would be the current output. Okay. And the next state, the current state. So from here, so what you can see is basically you can represent this as two fully connected components. Okay, so visually you have this is a one RNN kind of block. You have some function that's not time dependent. It has parameters, these weights. For example, weight matrices from x to y, or from x to h, okay, where h is the hidden state. So it's not time dependent, but it is parameterized. And the time dependence is generated by this state that's propagated through time. So at each point you can insert the current sample and the current state. Okay, and you get the new state, and you can use the next sample. Okay, that's the basic idea. Now, the most simple, basic, vanilla version of an RNN can be just specified like so. So you can see it kind of looks like two simple MLPs or fully connected layers. You have this first part, which transforms from x to the hidden dimension. So you have one matrix from x to h. You have another weight matrix from h to h. So you're taking the previous state into account here, and you're combining them, and you're getting the next state. This is just some nonlinearity. So you have this kind of affine transform here and nonlinearity, and to compute the output, you do the exact same thing but with different parameters. So I have this weight matrix from the hidden dimension that you just computed to the output. Okay, so that's very simple. It's only based on what we saw so far. This is a vanilla RNN. Yeah.
So you do this for each sample, right? With multiple layers of this, or where does the...
I'll show it. I'll show the layers. This is a layer, but you use it in multiple time steps. So this is what this shows. So if you imagine taking that single layer, okay, so again, that single layer is basically composed of two fully connected layers. You take that single layer and you unroll it through time, which means that you just reuse it. You're reusing it with the same weights and biases, the same parameters, but each time you're giving it a new input, and you're using the previous state. Okay, so you input a sequence of inputs, and you get a sequence of the same number of outputs here. Okay? And each time you had some kind of hidden state that you propagate. And the idea that this hidden state would represent all the knowledge that's encoded by the previous inputs and outputs. Okay? So if you have all this knowledge encoded as a hidden state, then your current output could depend on all the previous inputs and outputs. Okay, so this encodes everything that was before. Okay, so again, all these blocks are the same. They have the same parameters, same functions. They're just getting different inputs and propagating this hidden state. Okay, and since that you can kind of decide how you want to work with RNNs, they have various applications. You can, for example, decide that you're looking at well, in this diagram, the red block is the input tensor, and the green is the RNN, and the blue is the output. So you can kind of look at all these relationships. You can decide to give one input and then propagate the hidden state, and you say that I want to look at multiple outputs. You can do something else where you input multiple inputs, let's say multiple words. This is an example that we're going to see. Multiple words, propagate the hidden state, and then you get one output that you actually care about. For example, you want to use this to classify the sentiment in the phrase. Or you can do many-to-many, for example, text translation. Okay, and you can do it various ways. It's very flexible because you input a sequence and you get an output sequence, and you can decide how you want to treat the output sequence, what exactly it means for you. Yeah.
What's the difference between one-to-many and neural network? Because now we haven't got any. So what's the difference, basically?
Here?
Yeah.
That you're propagating this state. So you had one input, but you're kind of recursing with the next state each time.
Yeah, but you're not adding.
You're not adding new inputs, but the state is also an input. Okay. Not sure what the application is, but just it's flexible. Flexible. I'm sure there's some application. Oh, image captioning might be. So, for example, this might be an image, and you want to. This is actually a few nice papers work like that, where you input an image, but not directly the image, the features that some other CNN extracted from an image, and you give it to some RNN, some deep network that was trained like that, and it will produce a sequence of words that say what's in the image. Like, I don't know, a boy swimming in a lake. Okay, so you have one input, which is all the features that you extracted with your CNN, and you get an output, which is a sequence. That's an application example. So we're going to see a different application today. And the question is, if you have this kind of model, then if this is what you're doing, then how would you backpropagate? How would you backpropagate? I mean, you're taking a single layer, but you're using it multiple times. And you have multiple outputs at each time, okay? So think about what you need to do. Right? So the idea is that you have to calculate your loss based on all these outputs, at least the ones that you care about. So in some cases, maybe you only care about the last one. But generally, you care about possibly all of the intermediate outputs. And again, each green block here is the same function. It has the same parameters. Okay, so but you can think about it as the parameters at time t. And you can calculate the gradient of the loss with respect to each of these parameters, but at each time step. Okay? And then you can just accumulate the gradient for each parameter from all its relevant time steps. Okay, because again each of these different time steps had a different path to the loss. Okay, and all of them have to affect the loss. If you compute the gradient with respect to the parameters, you have to account for the time. So you have these different kind of gradient flows, and you have to account for all of them. And this is just unrolling through time, but basically it's the same one function. Okay, so you have a different gradient from each time step, and then you have to accumulate them. That clear? So you can think about it kind of like that. If you have some weight parameter w, and you calculate the gradient of the loss at time t with respect to that w, then you keep going with the chain rule, and you get to this part where you have to actually go back through the hidden state to the previous times, and you have to sum it from the initial time to the current time. Okay, this is kind of what's being shown here. That if you look at, for example, this time, it depends on all these previous times, and you have to sum all these gradients up to that point for each parameter. Okay.
Do you not introduce a new input until you finish calculating all the relevant gradients of the previous time step?
No, like the most vanilla way to look at it. Let's say you have your input is some text. You're working word by word. So you'd input the whole text. Okay, you have 1 million time steps, and then backprop to the whole thing. That's what you would do classic. But again, the question is how far can we go, and what's the limiting factor here? So what's the problem with this approach? That's the question. So can anyone see a problem, kind of with this backpropagation to time thing? Well, memory, yeah. Seems slow. That's one. And again, vanishing gradient. Yeah, you keep multiplying by, and the more time steps you have to keep multiplying by everything that was before. So basically the kind of the magnitude of the weights really determines how deep you can go. And if you kind of theoretically look at it, it's the eigenvalues of the weights that are determining. So if you have eigenvalues smaller than 1, that you will get a decay, and if you have larger than 1, that you might get an explosion. If you're working on models that are too deep, and in this case, when I say deep, I mean deep in time now. I'm not deep in depth, because this is only one layer deep. But the fact that you're deep in time causes again vanishing gradients, like in the case of depth, because of this kind of multiplicative effect here. So pragmatically, what do? We just say, let's not go all the way back. Let's say this is my whole book. I'm not going to go all the way back. I'm just going to go back until, let's say, the last sentence. I'm going to compute this loss. This is what I care about. I'm going to go back prop until here. Okay, and then start again, and then keep going. And the crucial thing here is to notice that the state is propagated. Even though I didn't go all the way back, this part is affected by the previous state. So when I have, let's say, after that I backprop and then I keep going with the rest of my book, okay, I will take the output state here and keep going. So even though I'm not backpropping to the whole thing, I'm reusing the state which should be a representation of all the inputs and outputs so far. That's the idea, at least, and this is known as truncated backpropagation to time. That's kind of the intuition. And of course, there are other ways to deal with this vanishing and hard to train problem. There are not non-vanilla RNNs, there are LSTMs and GRUs. You'll see this in homework 3 implementation. But here we'll show something else. Okay, and just like with regular networks, we saw that we unrolled one single layer through time, but you can also have multiple layers. So this is like each vertical here will be like an MLP, where you have multiple layers of depth in your MLP, but you're also unrolling through time. So for every time step, you have this multi-layer MLP, and you also have multiple time steps, and the dependencies are caused by these H's, these hidden states. So this is just an extension, combination between an MLP and the RNN vanilla layer that we saw. Okay, so now it's now the back propagation through time is even harder and even more vanishing. Okay? So you will train something like that in the homework, and you will have to deal with it with a kind of more advanced model. Okay, so let's look at an implementation of a simple vanilla RNN, just based on the above equations. Using PyTorch, let's implement our simple RNN. Okay, so let's see what we have here. We have our we have our input dimension, which is the input dimension, the hidden dimension, and the output dimension for y. So this would be for h, and this would be for y. And this is just what nonlinearities I want for h and for the output y. Okay, so you can see that I need these three fully connected layers, or linear layers. These are my weights and biases. So I have one to convert from x to h. This is the wxh. Okay, I have one from h to h. Okay, so this is my whh, and I have one from h to the output. Okay, remember in the first equation we had two affine terms, and in the second equation we had one affine term. So this is the first equation, this is the second equation. And the forward pass is really simple. Notice that I take both an x and an h. Okay, and if I don't have an h, I just use zeros. Okay, and all I'm doing is computing it using the formula that we saw. So I'm applying the first fully connected to h. So this is the xh. Now for every, I'm converting from the input dimension to the output dimension through this fully connected layer. So it's kind of like, it's like a matrix multiplication. And then another matrix multiplication with this fully connected layer for h, from h to the new h, applying a nonlinearity, and I get my final new h. Okay, then I take my new h, apply a fully connected layer from h to the y dimension, then I get my y. Okay, and optionally I can apply this nonlinearity on y. Let's say if it was a sigmoid, then I can then I can say that my y is interpreted as a probability. Let's say I want to do classification. Okay? That's it. Great. So that's a simple RNN. Let's see that it works. Like we saw, we have these parameters, which are just fully connected layers. This is one RNN, cell or layer. Remember that it's a layer because what you saw is unrolling it through time, right? But if you look at the vertical, from an MLP perspective, it's one layer.
Yeah, but we're looking at one box.
One box, it's a layer. From the perspective of the vertical part, it's a layer. Okay, and you're using the same layer with the same parameters multiple times in different time steps. Okay, it's kind of a bit confusing at first. All right, so I have this RNN layer. Let's see that I can manually input a few time steps. So I have this just random I have a batch here of random numbers with my input dimension, and I'm applying my RNN. I'm getting the first y and h, okay, and then I'm taking this first h and creating a new input for that, and getting y2 and h2 and so forth. This is just a manual kind of unrolling through time. You can see that I'm getting just what I expect. So I have a different dimension for the hidden. Everything here is a batch, okay? So I define the output dim as 1, and the hidden dim as 10, and a batch size of 3. So I should have said that. So you can see I have 3 elements here with an output dimension of 1. And so for the h, I have 3 with the output dimension of 10. Okay, so that's it, just showing a manual forward pass. Okay, so let's move to the more interesting part. I want to show an application example. So what we're going to do is try to analyze movie reviews and decide what the sentiment is. So our task is to get a sequence of words, for example, best movie ever, and say whether it was positive, negative, or neutral. Okay, I want to have this classification. So if you just look at words alone, it kind of might be difficult. For example, look at this review. So if you say this movie was actually neither that funny nor super witty, so if you just look at words like witty or funny, you might argue that it's a good review, but you have to actually have context. You have to understand that this this negates that, and this word negates that. So you kind of need some kind of a sequence of words and maintain a state and a context that will allow you to understand that this is negative. So maybe an RNN will fit here. Okay. So you will use a data set from a package called torchtext, which provides tools for working with text and various data sets. So there's this data set called the Stanford Sentiment Tree Bank, which has about 10,000 labeled movie reviews. Okay, and our labels are positive, neutral, or negative. Okay, so I'm gonna quickly go over the data loading. It's not very interesting, okay, and might help you. It might be a good example, so it could help you later on. But I want to focus on the model parts. So basically, what's going on here? I'm creating these two objects called field, and what they do is they act like parsers and tokenizers. They take, in this case, they will take a review, and they will split it into words or symbols, and they will add some special tokens that represent the beginning and end of the sequence. Okay, and I have another field here that takes the label, for example, positive, negative, neutral, and converts it to a number. So this is not very interesting. I don't want to focus on that. I'm just going to show you that I have this built into torchtext. I have this SST database, and I give it my parsers, and it uses those parsers to create my data sets. Okay, so these are regular PyTorch data sets, and I can check that I have, for example, 8,000 training samples. Okay, sorry, didn't need to run it again. Okay, so let's look at the data a bit. So I'm just taking some random indexes here, and I'm taking the training data at that index and printing it out, just so you can see what we have. So we have sample number 111 is positive. This film aims to be funny, uplifting, and moving, sometimes all at once. Notice the spaces here between the punctuation. This is because we had this parser that applied the tokenization scheme, and if it sees a comma, it does not join it with this word, because we want to represent words. It should be, the fact that there's a comma should not affect our representation. So the word is funny, and it gets a different token than the token of comma. So we separate it to two different tokens, and each token will have a number in our vocabulary, which I'll show in a second. So this is just examples from the dataset, just to show that it works. And we build a vocabulary, which is a bidirectional mapping. So imagine that we take all the words in our dataset. For each word, we just give it an index. Let's say the word hello has an index of 100, and it's not exactly word, it's actually all these tokens. So the token comma or period will also have an index. Okay? So this is what the vocabulary means. So number of tokens in the training is 15,000, so we have 15,000 different words or tokens. Okay? Let's see some tokens. So the first 20 tokens are, some of them are special. We have these special tokens: unknown, padding, we'll see why it's used later, start of sequence, end of sequence, then period, and the. I think this is also ordered by frequency. So, for example, period is very, very common, so it's one of the first ones, and the word the is very common, and so on. The word film is obviously common for movie reviews. Oh, sorry. Okay, so these are the tokens, and we have these special tokens. So the index 0 to 3 are special tokens. We'll see them in a second. Okay, and I can see that if I take my vocabulary and I convert S to I, string to index, some random words that I imagine that would be in the reviews, then I actually find these reviews and I can say what the index of the word is. So this is just to show you what the vocabulary is building. Okay. And for the labels, we have positive is 0, negative is 1, neutral is. So again, the idea is I take lots of text, I convert it into a vocabulary of words. Each word has a number that represents that word. Okay, that's the bottom line. Think about it. You need a way to input text into an RNN. RNNs work with, actually not even numbers, they work with tensors. You have to have some kind of tensor input. Okay, so that's the next step. How are we going to get some kind of tensor input that represents each word so that we can use it as an input? Okay, the next thing that we need is a data loader. we're working with text sequences, and we want to batch them. We want to take a batch of reviews. But again, reviews, they have different length, different number of words, different number of characters. Tokens, sorry. So different number of words mean different number of tokens. So our batch has to be able to deal with the fact that we have samples of different length. So the time dimension of each sample will be different length. So there's a built-in data loader called the bucket iterator that I used here to do that. I'll just show you what it's giving us. If I look at a single batch. Okay, so I'm taking a batch from my data loader now, and I'm looking at the text and the label. So this is my text. As you can see, it's now represented as a tensor. And the dimension of this tensor is 21 by 4. And my batch size is 4. Okay, so what's this 21?
Sentence length.
Exactly, the sentences, but I have 4 different sentences. So what length?
The maximum. Longest.
Exactly, the longest one, and the rest are padded. That's why they all end with this 1. So remember, the 1 is the index of the token pad. Pad is a special token, so we had pad, EOS, SOS. So this is just padding the ones that are not that are not long enough. And I think 3 maybe was period or something, or 4 maybe was period. So that's why these are ending with 4 and 3. And the rest of these numbers here just represent different words. For example, maybe 1227 is the word hello, okay, or something like that, or word film. So now I represented 4 movie reviews as this tensor. Okay, that's what's going on here. Okay, clear? Okay. So, and also notice that the first dimension here was not batch. As opposed to what we saw so far, usually the first dimension is the batch dimension. Now the first dimension was the sequence dimension, the time dimension. Okay? So it's different, and you'll see why in a second. This is the usual convention with RNNs. Let's look at our model now. So we'll base it on the vanilla RNN layer that we implemented before. Okay. So we'll take a batch of these tokenized sentences that I just showed you. So you have a sequence length, some of them are padded, and a batch dimension. And then we will compute the dense word embedding for each token, okay, and process the sentence sequentially. So we'll go time step by time step, feeding our words or a batch of words into the RNN, okay, and getting an output. Finally, we'll look at the last output and treat it as a probability over 3 classes. So just this part here, we have to compute the dense word embedding. So I think you saw a video about this. So what is a word embedding? Yeah.
You look around the word and try to inference from it what the meaning of the word. Connection.
Well, it doesn't have to be meaning. It's just a way to represent a word. You take a word and you want to represent it as some kind of vector. Usually you find representations that are semantically meaningful. So yeah, maybe words that are similar will be represented close by in some space using some metric of closeness. But the idea is, just for our purposes, convert from a word, in our case a word is an index of a word, so 1400, to a tensor representing that word in some semantic space. So usually you take some pre-trained embedding. Someone trained an embedding model like you saw in the videos, and we just take that embedding model. Here we'll just train our embedding together with the model. So we have this embedding layer, and it takes 2 parameters, non-embeddings, which is the number of different, in this case, words, number of different things that we want to embed, and the dimension of the embedding. Okay, and so it will. Yeah, I have a vocabulary of 5 different words. I want to create an embedding of dimension 8 for each of those. So let's see how it works. I'm taking an embedding layer and I'm inputting here 10 a tensor of length 10, which is just random integers between 0 and 5, or 0 and 4 inclusive. So that's why I have 5 different values, possible values for word representations, and what I'm getting back is just something with dimension 8. Okay? You can think of this like a lookup table. You give it an index. Let's say the index was 0, which is the first word in the vocabulary, and it will give you back some representation of 0 as an 8-dimensional vector. But the thing is, this is something that you can learn. You can learn these parameters. This is a learnable layer, and all these vectors inside this embedding are learnable. Okay, so this is how we can train an embedding. It's not the best idea for the sentiment analysis task, but I didn't want to use a pre-trained embedding because I wanted to show you this this concept of how to train it. So is it clear what the embedding is doing? I can maybe show you if I find this. Just think about it like this is the embedding matrix, and we have indices of the words like from 0, and let's say I have 100 words. Okay, so just for each index of a word, I will get a tensor of some dimension d, the embedding. And when I give it a word, I just get this tensor back. It's like a lookup table, but it's a tensor that tracks all the operations, and you can calculate its gradients. And when you train your model, this will actually be updated. So you're updating your embedding when you're training the model.
So how we so besides the initial
It's just random. You can specify more parameters here to specify specific initialization, but usually just yeah, I'm just showing you something that will be a part of the model, the embedding. Because like I said, our model I will have to learn it, yeah. Like I said, the model will take an input, compute a dense embedding, then process it sequentially with an RNN, and then produce an output. So I need this embedding as a pre-processing step to actually use my RNN, because my RNN wants to get a tensor. And I have indexes of words, and I need to find a way to make it work. So I need to convert from indices to words to some tensor, and then give it to my RNN. Okay, so now let's look at the actual model. So this is the whole thing. Let's look at what it's doing. It's taking this input dimension. Okay, we'll talk about it in a second. The embedding dimension is the the size of this dimension that I want here. Okay, the hidden dimension for the RNN hidden state, and the output dimension depending on my task. In my case, it would be 3. I want to do a classification task with 3 classes, so my output dimension should be 3. I'm creating this embedding layer like I showed you just now. So from input dimension to embedding dimension, this will give me my embedded word vector. Then I have this RNN layer, which we implemented ourselves just not long ago. Okay, its input dimension will be the embedded dimension. It will compute hidden representations with this dimension, HDIM, compute this output dimension, okay, and I don't want any nonlinearity on the Y. Okay, I want just raw class scores, not probabilities in this case. And then I have this log software which I will use to compute log probabilities. Okay. In my forward pass, I'm taking X. Now X is what we got from our data loader. Remember, so we had sequence length by batch. This is my X. Again, batch dimension is not first. I'm embedding X. So now for every number there, what we had, let's say we had the number 1000 for representing a specific word, I'm getting this embedding. Okay, so it's like converting, I had S by B, okay, and now what this embedding will do is kind of give you the third dimension. If the original matrix had 5 here, and 5 was the index of the word, then now you'll have this new representation of that word 5 as an embedded vector. Okay, that's what you get. Now this is actually going over the time now. Okay, I have to loop over my batch, but over the time dimension. So this is actually why it makes sense to have the sequence dimension first. When I do this, when I'm looping over embedded and saying this is xt, what I'm getting now is that xt would be what shape? What shape is xt? B, no, it would be B by E. I'm looping here over the first dimension. Okay, so I would get xt will be b by e. So now I have a batch representing a single instance in time. So the first xt would be the first word of the 4 sentences. The second xt would be the second word of the 4 sentences. Okay, this is how I work with batches, but also do the RNN sequence thing. Okay, so I have to go over time steps. So I have to have this loop to process it sequentially, because at each time step I have to give my RNN the input and get the hidden state, and this hidden state will be propagated to the next time step here.
Wait, the S is the, like, in the drawing you made on the board.
So this is S,
Yeah.
the length of the longest sentence in the batch.
For each row is,
Yeah, so I'm going over each row, exactly. So each row will be this 2D slice inwards. Okay?
each row is a sentence.
No, each row is a time. Let's say this is 3, so this is the third word of all the batch sentences. Okay?
But where is the time shift?
The for loop is going over the times. That's why I call it xt.
So it goes on rows?
Yeah, it goes over the rows of this. Each row of this 3D tensor is this 2D slice. Yeah. Have to think in tensors.
You're building the vertical layer, right?
Yeah, I'm going sequentially through time, but I have to work with batches, otherwise it would be not efficient. So the way I use batches is like you did in the FC case. The batch dimension now is first. When you have xt, right, the dimension of xt would be b by e. Okay, so b by e, batch dimension is first, and then you can apply the weight matrices as a usual FC layer.
B by E is just the same information extended?
No, it's not the same information. I have b is the number, the batch says, I have 4 different sentences, and I took the third word from all 4. Okay, so I'm processing it together like that.
So what's the dimension of the sentences?
Dimension of the sentences is s. This is the length of the sentence, or the longest sentence.
No, the dimension of the number of the sentences is
B. B, batch size. Number of sentences is batch size.
Okay.
Okay.
Wait, but when you're calling the self-RNN, you're not building a cell of RNN, you're calculating.
It's a cell. I'm using the same layer with the same parameters over and over again.
Yeah, but you're not now building the graph, you're now pumping concrete numbers and getting the results.
This is exactly what was drawn before when you had multiple blocks like that.
Yeah.
Okay? This is exactly that. This implements exactly that drawing. That's the idea. I'm showing you in code now what was theoretically a drawing before.
Sounds like you're looking at a single unrolled block, which is processing 4 different
Sentences.
T.
Yeah, yes. No, it's processing one time step,
Yes.
but 4 different sentences. Yes, exactly. Okay, and again, you'll do this yourself in the homework and you'll have fun, so you really understand. I have to keep going because we still have stuff to do. So this is our model. Okay. As you can see, all it has is an embedding and this 3 RNN layers, or 3 fully connected layers inside our RNN. I'm going to use an embedding dimension of 100, hidden dimension of 128, and the output is 3 because we have 3 classes. Okay, let's see a forward pass. Let's see if it makes sense. We took our X, which had 4 sentences, right? And we got 4 tensors with 3 elements here. So this is the class probabilities or log probabilities, because we had a log softmax at the end. So these are log probabilities for the first sentence. Okay, so first sentence, log probability of positive, negative, or neutral. Sorry. Okay, let's see how big our model is. This is a function just to count the parameters. So we have 1.5 million trainable parameters. That sounds kind of like a lot. All we had is 3 fully connected layers. So try to think for a second, where are all these parameters? Why so many?
You have 3 metrics in each RNN.
Yeah, but the RNN itself is very small. It's not, it should be So where are most of the parameters?
Coming from the embedding.
The embedding, exactly. Because the embedding, you have the dimension here for the embedding matrix is the number of words. So we had, I think, 15,000 words or something like that. And for each word, I have 100D tensor. So this is most of the parameters by far. You can see it's about 1.5 million parameters. Yeah.
Can you explain each time you load a batch, you work on a new batch, the S is different, right? Like you take 4 sentences.
Yes, S is different each time.
It's like for different number of T's you train it.
Yeah.
And it's not a problem.
No. No, not a problem. That's the point of RNNs. You should be able to work with sequences of any length and produce a sequence of the exact same length. I have to keep going, so you can ask me after the tutorial. Okay. All right. So let's just show the training now. So there's nothing interesting here. I'm gonna skip it. It's the exact same training loop that you're used to seeing. Okay, forward pass, backward pass with zeroing. Just using the backprop from AutoGrad and calculating optimizer step. This is a function that I'm going to use after that for the second model. Okay, let's run it. You can see I'm just creating a sentiment RNN model here. I'm taking some optimizer, and my loss function will be negative log likelihood because we had log softmax. So we have log probabilities, and this is what this expects. It's like cross entropy on the raw scores if you use the PyTorch cross entropy. Okay, so you can see it's kind of training. Loss seems to be going down, so that's nice. Great. Right, so let's keep going. Using kind of pre-trained embeddings is a much better idea because you're wasting a lot of time training these embeddings. And like I said, there are much more efficient RNN units that you can train them much easier. But so don't expect state-of-the-art results with such a simple model. But the fact is that it works. It gives you kind of a feeling for how to work with text and how RNNs work, kind of on a low level, because you see the actual unrolling of the time steps. So now let's look at a different way to do this with a much newer approach called temporal convolutional networks. So the thing with RNNs is that they're very hard to train. Like I said, the longer, if you have really long sequences and you really care about the dependency of the end of the sequence to the start of the sequence, then you never actually use some simple RNN. You use a very complicated version of an RNN, like you'll see in the homeworks. And like you saw that you have to process sequentially over the time steps, you need that loop there. You saw the implementation had this loop. So you get poor performance because of that, and you get poor optimization because of the way the whole thing is defined and the backpropagation through time works. So can we use convolutions to do the same thing, to work with sequences? That's the idea. Because CNNs are much better, easy to train, relatively easy to train, and they look at the whole input. So can we use them instead? So the things we have to deal with if we try to use CNNs is that, first of all, we need to find a way how to do this sequence thing. So we need the input and output to be sequences of the same length. Okay? And the length should be arbitrary. So we need to be able to deal with input of any length. And in this case, length would be like if we had images. So length here is the spatial dimension. Let's say we had an image. So now we just have 1D. Instead of a 2D image, we have a 1D image. That's kind of our idea. Okay, and we treat the spatial extent as the sequence. We need the output at time t only to depend to inputs up to t, and we need some kind of way to model these long-term dependencies across time. So let's talk about that a bit in the context of what we learned so far about CNNs. So if you want the input and output to be able to deal with kind of arbitrary spatial extent, we saw that fully convolutional networks are a way to do that. Okay? And if we use appropriate padding, we can kind of keep the same length. Remember that if you choose the parameters of the CNN appropriately, you can keep the same spatial extent. So that's one thing. And we're talking about 1D convolutions now. And again, I did kind of mention it, but the fact that there's a 1D or 2D, like in the code that we saw, 2D conv 2D means that feature maps are 2D. Okay, not the kernels. So now we're going to use 1D convs, which means the feature maps are 1D. which means we have just a one-dimensional sequence, like one row from an image, for example. And the output at time t should depend on inputs up to t, so we have this concept of causal convolutions, where the output is only convolved with elements that came before. I will show it in a second. So there's a causal version. And to model these long-term dependencies, we saw a concept called receptive field, which is something that increases the effect of the input. As you go deeper, you have a larger region of the input that affects the activation as you go deeper. And we saw that you can facilitate it either by depth, and now as you saw that we have these residual collections that allow you to get deeper. And we also saw that convolutions can be dilated. And dilated convolutions are another way to increase the receptive field, because you're applying your same filter on a larger activation space of the previous layer. So using these three techniques, combining them, you get something called a TCN. TCN is a temporal convolutional architecture. So the idea of a TCN is, like I said, combining. We have two elements here. First of all, dilated convolutions. So let's say this is our input sequence. Okay, and now again we're treating the spatial extent as time. Okay, just arbitrarily. Spatial extent is time. So this is my convolutional kernel. It has spatial extent of 3. It's going over all the channels. Channels are not shown here. So I have this convolutional kernel that I'm sliding. I'm using padding to get the same spatial extent layer by layer, and dilation to apply my convolutional filter with these skips. So I'm getting a receptive field that's growing very, very quickly with depth. Okay, and the fact that it's the causality of the convolutions is due to some kind of chopping the rest. Remember, padding should be also here, but you're just not looking at what's in this area. So basically, you're just saying that to compute this part, you're convolving with the current time and all the previous times. Okay, it's just kind of a way to look at how you're doing the convolutions. And when you add padding, you can get the same spatial extent. Okay, so you can kind of see in this image why it's causal, but if you don't really understand what's going on, then try to just draw an input sequence with padding on both sides, compute what you would get, and then see how you need to chop it to get this effect of causality and the same input sequence length. So this is just regular convolutions on one dimension. And the second part is this residual block. So the TCN architecture, or at least one type of TCN architecture, is to have, so we have a dilated causal conv, which is this. Then we have some normalization. I'm not showing it in this example. And ReLU and dropout. Another convolution, dilated. And again, ReLU and dropout. And this skip connection. See? Okay, so this is the residual connection that we saw in the previous tutorial for ResNets. So combining these two ideas, we can get something very powerful. Okay, so let's begin with a general TCN block, and then create a TCN for sentiment analysis. So this is our general TCN block. Let's go over this for a second. Like any kind of convolutional block, you have to define input and output channels, kernel size. This time we'll define dilation and padding. So we have, in our block, we'll have 2 convolutions, okay, like it's shown here. I just implemented this thing without the weight norm. So my first convolutional part would be a sequential of conv, 1D conv, because my feature maps now are 1D, from input channels to output channels, kernel size, stride of 1, okay, padding, and the dilation of the input that I got, just the parameter. Okay, another conv from output channels to output channels, so I can chain them. This output channels here goes here. Okay, and then again, both of these cases I'm applying ReLU and dropout. And for my residual connection, I will sometimes need this extra thing, this extra convolution for adapting the number of channels on the skip. You can see, I explained it also in the previous tutorial. You can see here sometimes the number of channels is not the same between the input and the output, so you need to add some extra convolution here to combine the input channels and change them to the number of channels of the output. Okay, the forward here will be just apply the first convolution. And then this is just taking the last part of the sequence. After you convolve, you get a longer sequence. Okay? And what this is doing is just chopping off this part here. Just chopping this off, the last part here. And maintaining the part that's causal. The part of the convolution that's causal. Again, it's kind of hard to show this, to explain it. Just if you just draw the convolutions, like in the previous example, you can see that you always have to just chop the padding from the last part of the convolution. You get this causality and you get the same length. Now the skip connection. So the skip connection, I want to add this identity mapping to my output of the two convolutions. So I have first convolution, output, then convolution 2, and then output. I want to add them, but sometimes they might not be able to be added because the channels are not the same. So if I define the channel adapter here, because I had a different number of input and output channels, then I will have a channel adapter, and if I have it, I will apply it to my input x. It will change the number of channels just by combining the input channels and creating new output channels. It's a 1-by-1 convolution. As you can see here, kernel size is 1. It's a 1-by-1, so it's not looking at any spatial extent. It's just looking at the channels. We saw 1-by-1 convolutions previously. And that's how I get my skip connection, and you can just join them. So this is a general TCN block. And once I have this general TCN block, I can build the sentiment TCN, which is really, really similar to my RNN. I start with this embedding. Okay. Once I have this embedding, I specify that the embedding dimension and all these other optional hidden dimensions are the number of channels in my TCN until I get the output dimension. And the output dimension is 3. So I will get, in my case, I will get 3 channels in the output, and I will treat those 3 channels as the probabilities that I care about. So what this code is doing is just building TCN blocks. You can see it's increasing the dilation by 2 to the power of the number of the layer. So I'm getting a exponentially increasing dilation, each TCN block. And I have multiple blocks. Each block is converting between my channels, so from embedding to the first channel, and from the second channel to the third channel, and so forth. And that's it. After that, I have a log softmax. So all I have to do is embed and apply this TCN. There's just some small trick here. Remember that when you embed, you have this dimensions, SBE, as you saw before, sequence, batch, and embedded dimension. And I want to convert it to what convolutions care about, which is batch dimension first, then channels, then spatial extent. So I'm doing 2 transposes here. Okay, it will transpose it to be batch, then channels, and then spatial extent. Okay, that's the whole trick here. Once you do that, your conv 1D will work on the spatial extent, but look at all the channels, and the channels initially are the embedding dimension, and then you just transform it to the different number of channels in your hidden layers, and finally to the number of channels 3, which is the number of classes that you have. Okay, so that's it. Notice that there's no loop here. I'm just taking my whole embedded X with all the time steps, getting my output sequence in one forward pass, and then I'm taking YT, which is just the last one. It's just the last one from here. It's the last sequence. So I have batch dimension by D out channels, and D out is the 3 that I care about. Okay, so I just did everything without a loop. Okay, and then I can apply my log softmax, and then I get probabilities in the channels. Okay, that's the whole thing. And basically this is it. The rest of the code is just showing that it runs and you can train, and it's a bit faster. Any questions about that? Okay. I recommend you go over the code a bit more slowly. I think if you compare it to the RNN, it should be clear. Thanks.